So let's proceed to our sample problem number 1. Design of laterally supported beams. The floor of a building consists of a 0.1 meter thick concrete slab supported by beams which are fastened to the web of girders and columns. So meron tayong thickness ng konkreto na 0.1 mm na magsisilbing slab ng ng floor natin. Design the beams and girders for the given dead load and live load of 2,400 Newton per meter squared in accordance with the AISC specifications. So we have given down na dead load at saka live load is 2,400 Newton per meter squared. So, Newton per meter squared is in Pascal. So, ang gagawin natin siyang kilopascal, that will become 2.4 kilopascal. Sabi dito, AISC specifications tayo. So, lagay lang natin. AIS specs. And at the same time, yung gagamitin natin steel is 836. So, AISC specifications. And yung steel natin is A36. So, para malaman ninyo yung Fy ng A36, ganito lang yan. So, let's say nakalimutan ninyo or hindi given sa problem, para mahanap natin yung Fy ng A36, yung 36, i-multiply mo lang siya, eto sa mga huli, i-multiply mo lang siya by 6.9. So, Fy is equals to 36 multiplied by 6.9, we have 248.4 or 248 na lang megapascal. The limit the deflection to L over 300. So deflection daw, yung allowable natin is L over 300 lang. The weight of concrete is 23,580 Newton per cubic meter. Yung usually yung mga steel natin, we have 200 gigapascal. Assume the beams and girders to be laterally supported. So yung beam natin at saka girders laterally supported dyan. So, ito yung girder 1 natin. Yung girder 1 natin, kine-carry niya yung dalawang beam, which is etong B1 at saka B1. Then, yung B2 natin, ito yung mga outside beams natin. So, G1 to, at the same time, yung nasa ilalim na girder, etong part na yan, that is also G1. Girder 1. So first of all, bago tayo mag-solve, first step natin is alamin muna natin yung mga loads natin. Let's determine the superimposed loads carried by the beam. So step number 1. So let's say that is step A. So ano step A natin? Yan. So next naman nun is we have ano yung mag-a-act aside sa dead load at saka live load na sinabi sa problem. Siyempre, ike-carry ng mga biga natin yung bigat ng slab natin. So, yung weight ng slab natin. So, para malaman natin yon, yung multiply lang natin yung unit weight natin sa thickness, wherein yung thickness natin, that is 0.1 meter, that is the thickness of our slab. So, multiply lang natin yung weight dito sa thickness ng slab natin para maging Newton per meter squared siya, para maging pressure. So, we have 23,580 Newton per cubic meter multiplied by the thickness of the slab, which is equal to 0.10 meter. So that will become 2358 Newton per meter squared or 2.358 kilo Pascal. So, kunin natin yung total load natin, pag-add lang natin yung DL plus LL at saka yung weight ng slab natin. So, total load, let's say WT o yung ano natin, kunin muna natin. So, let's say total load is equals to 2.4 kilopascal plus etong 2.358 kilopascal. So the value of our load is equal to 4.758 kilopascal. So kapag sinabi nating pressure, so meron tayong given na area, tapos sa isang area, let's say etong area na to, etong slab na to, magkakaroon tayo ng mga forces. So kung titingnan natin yan sa 3D, so i-3D lang natin. So let's say etong slab na to, etong part yung nasa gitna. So i-3D lang natin. So let's see pag ganyan siya. So eto yung slab natin na nakapagitna. So meron tayong tinatawag na pressure. Yung pressure na yon is acting siya on the entire area. So in this example, eto, meron tayong pressure sa kada points or the entire area itself. So sa kada area, dun sa gilid, dun sa gitna, pati sa gitna dito, meron tayong mga forces na acting dito. On the entire area, meron tayong pressure na naka-apply. So, yung problema lang natin dito is, paano natin nahahanapin yung uniform load na mag-a-act dito sa B sub 1 natin. So, since yung B sub 1 natin, kung mapapansin ninyo, etong slab na to, and dun sa kabila, that is a one-way slab. Meaning to say, yung kalahati ng loadings natin dito sa kalahating slab. So, eto. Tsaka yung kalahati dun sa kabila. Ayan. So, etong kalahati nito is kalahati ng 3. That is 1.5. Kalahati ng 3 sa kabila. That is 1.5. So, 1.5 plus 1.5. We have a tributary height of 3 meters. So, yung height na to hanggang doon, that is equal to 3 meters. So, ito yung dadalhin ng beam 1 natin. So, para makuha natin yung total load na mag-a-act dun sa B sub 1 natin, which is yung etong WT, sabihin natin WT, so that will become 4.758 or the total load kilonewton per meter squared. Multiply natin siya dito sa tributary width natin. Yung tributary width natin is 3 meter. Meaning to say, kapag minultiply natin yung load natin na 4.758 dito sa 3 meter, meaning to say, sa kada meter, sa kada metro, dito sa tributary area na to, meron tayong, dun nag-e-exist yung W sub T natin. So, let's say that is 3 meter. Mangyayari, magiging kilonewton per meter yan. We have 14.274 kilonewton per meter. So, meaning to say, sa kada metro, meron tayong 14.274. Or in other words, sa kada meter dito sa tributary area natin, meron tayong 14.274. So, dito, tsaka doon. So, kung i-consider natin yung loading, isa-separate natin yung B1 natin. So, ito yung B1 natin. So, meron siyang length na equal siya sa 6 meter. So, that is 6 meter. And yung load natin, that is WT sub T is equals to 14.274 kilonewton per meter. Next na isosolve natin is the maximum shear and the maximum moment. So, paano natin isosolve yon? So, let's step 2 natin. So, since it is a simply supported, so, mangyayari niyan, yung Mmax natin, that will become yung WL squared. So, that will become WT L squared all over 8. So, yung WT natin, that is 14.274. Multiply natin siya sa L squared, which is 6, all over 8. So, the value of our Mmax is equal to 64.233 kilonewton meter. And also, we have the Vmax, or the maximum shear, that is WL over 2, which is equal to yung 14.274, multiply natin by 6 divided by 2. So, Vmax is equal to 42.822 kilonewton. Next naman is, meron na tayong given na Mmax at saka Vmax. So, sa next step natin, since nagde-design tayo, kapag nagde-design tayo, we always begin with an assumption. So, lahat nag-i-start sa assumption. So, in this example, sa still design, kapag nagde-design, lagi nating ina-assume na laterally supported yung beam natin. So, let's say, or let's assume, for our step number 3, assume compact section. So, kapag compact yung section natin, meaning to say, yung allowable bending stress is equals to 0.66 Fy. So, kung matatandaan ninyo, yung actual natin o yung small f, so kapag small f, that is actual. Kapag capital F, that is yung allowable. So, yung actual natin, that must be less than dapat yan or equal sa allowable para maging safe yung structure natin. So, since allowable, ASD, allowable stress design, meaning to say, ini-equate lang natin yung allowable dun sa actual. So, in this example, yung goal natin is mahanap natin yung section na gagamitin natin or the trial section. So, since wala tayong given na mga dimensions, so, hahanap tayo. Gagamitin natin yung ASEP Steel Handbook. So, kunin muna natin yung allowable. Yung allowable bending stress natin, that is 0.66 Fy, which is equal to 248 megapascal. So, the allowable is equal to 163.68 megapascal. So, para mahanap natin yan, di ba meron na tayong allowable, equate lang natin siya sa actual. So, FB is equals to yung Mmax natin all over yung SX natin. Or yung SX natin. So, etong M na to, that will become the M maximum. So, makukuha na natin yung value ng S of X natin. Yung M max natin, that will become 64.233. Kaso, naka-megapascal yung stress natin. That's why, kailangan natin i-convert to into Newton millimeter. So, imumultiply lang natin yan by times 10 raised to 6 para maging Newton millimeter yung unit niya. All over the allowable na 163.68 megapascal. So, yung SX natin, we have 392.43 times 10 raised to 3 millimeter cube. So, ulitin lang natin yung step 3 natin. Nag-assume lang tayo na compact section para mahanap natin yung value ng S sub X natin o yung section modulus natin. Next, for the step number 4, maghahanap tayo ng trial section. So, yung trial section na to, kailangan yung SX na, yung trial section na to, kailangan is maging close or greater than siya dapat dito sa nakuha nating section modulus. So, hahanapin natin yan sa ASEP Steel Handbook. So, yung trial section, hahanapin natin sa ASEP Steel Handbook. Kaya nga, nire-require ko kayo na magkaroon ng ASEP Handbook. Kasi, ibe-basis natin yung S sub X. Ngayon, yung hahanapin mong trial section, dapat equal siya dito sa nire-require natin na S sub X or greater than siya. Diba? So, itong trial section natin, dapat mas mataas siya dito sa nire-require natin sa problem or equal. So, kung hahanap kayo sa ano natin, since nag-undergo tayo sa AISC specifications, yung ano natin dito, kailangan kapag sa AISC specs, kapag laterally supported, for laterally supported, yung minimum D natin, so yung minimum D natin, that is L over 20. Or yung may minimum na L over 20. So yung L natin, that is 6,000. Or yung length ng beam natin, all over 20, is equals to 300 mm dapat. Dapat greater than dyan or equal sa 300 mm. And at the same time, yung thickness ng web, kailangan 6 mm siya, according sa AISC specifications. And at the same time, meron tayong dito sa nakuha natin na S sub X na 392.430 times 10 raised to 3 cubic millimeter. So, etong dalawang to, eto yung sa AISC specifications for laterally supported beam. So, kailangan nating humanap ng trial section sa ASEP Steel Handbook natin. So upon checking sa ASEP Steel Handbook natin, yung let's try etong W12 by 22. So, etong first requirement natin, dapat yung S sub X no trial section natin is greater than or equal dapat siya dun sa S na nire-required natin. So, in this problem, yung S required natin, eto yon. Ito yung S required. So, nire-require natin is 392. Eh, yung nakuha nating trial section is 416. So, malapit lang siya sa 392. So, kapag kumukuha kayo ng trial section, kailangan close enough dun sa S requirement natin or dun sa nire-require nating X. So, yung goal sa pagkuha ng trial section is kailangan nating ma-add yung weight ng biga natin. So, sa pagkuha natin sa unang example, diba, sa step number 2 natin, or the step letter B, hindi natin na-consider yung weight ng beam natin. Kasi nga, dinidesign pa natin yung beam. Hindi pa natin alam yung dimension ng beam natin. So, in this example, i-add natin yung weight ng beam natin. So, we have yung weight ng beam. Weight of beam is equal siya sa 33 kilogram per meter. So, imumultiply natin yan by gravity para maging siyang Newton, 9.81 meter per second squared. And, i-divide natin yan by 1,000 kasi nga, magiging Newton yan. So, magiging Newton per meter lang yan. So, i-divide natin yan by 1,000 para maging kilonewton. So, Newton meter, i-divide natin by 1,000 para maging kilonewton meter. So, yung weight ng beam natin, that is equal to 0.324 kilonewton per meter. So, yung bagong W sub T natin, sabihin natin W sub T prime, i-add natin yung weight ng beam. So, 14.274 plus yung, etong 14.274, wala pa yung weight ng beam dyan. So, i-add natin yung weight ng biga natin na 0.324. So, that will become 14.589 kilonewton per meter. Next naman, tapos na tayo sa step 4 natin or the step letter D. Ngayon, i-check naman natin kung compact or non-compact yung section natin. Diba? Sa step number 3 natin, in-assume natin na compact section. So, after assuming, kailangan patunayan natin that our assumption is correct. So, ngayon, sa step letter E natin, patunayan natin, di ba? Or patunayan natin na yung section natin compact. So, let's check if section is compact or non-compact. So, check muna natin kung non-compact, kung compact siya. So, sa pagkuha ng check for compactness, so yung mangyayari doon is aasa tayo doon sa properties ng material natin. So, ito yung BF all over 2TF. Dapat, that is less than dapat yan. Diba? Di pa natin alam. Dapat maging less than yan sa 170 over square root of Fy. And also yung D all over T sub W natin. Dapat, that is less than siya dapat sa 1680 over square root of Fy. So, check muna natin, no? Kapag nag-govern yan, ibig sabihin, compact yung section natin. So, erase muna natin itong nasa babang part natin. Check muna natin siya, no? BF all over 2TF. So, what is the value of our BF? So, makikita nyo doon. So, that will become 102.36 all over yung TF natin, that is 10.8. So yung 170 natin over square root of Fy, which is 248. So that will become, eto, kung isi-simplify natin, that is 4.739. And eto naman, that is 10.8. Since it is less than, therefore, pasado tayo dun sa unang test natin, dun sa unang checking. So proceed tayo dun sa susunod. So yung D natin, that is 312.67 all over yung thickness ng web natin, which is equal to 6.60 and 1680 over square root of 248. So hindi pa natin alam. So natin, that is 47.37 and ito is 106.68. Since it is less than, therefore, compact section or assumption is correct. Assumption correct. So since na-prove na natin yung assumption natin, so let's proceed dun sa sa pag-compute ng weight ng beam natin. So that will become yung step number 6 natin. So lagay lang natin yung weight ng beam natin, which is na-solve na natin dito. That is, so kunin natin yung total weight. Total weight, di ba? Including weight of beam. So that will become yung W sub T prime natin, which is equal to 14.589 kilonewton per meter. So next naman for our steps, di ba? Sa mga last steps natin, i-check na natin kung safe ba sa flexure, shear, deflection yung beam na dinesign natin. So let's check. So check natin muna sila. So una, syempre, i-check muna natin sa flexure. Pangalawa sa shear. So pangatlo sa deflection. So F, so sa step number 7 natin, so let's say letter G, check for flexure. So that will become etong actual natin o yung small f, dapat less than or equal siya dun sa allowable natin. So nakuha na natin yung allowable natin. So FB, so yung actual natin, that is equal to M over SX. So yung M natin dito, since kasama na yung weight ng beam natin, magbabago na. So solve na lang natin. So shortcut na lang, no? Shortcut na lang natin siya. So that will become 14 point, since it is simply supported, WL squared over 8,589. So that is, so WL squared over 8, WL squared over 8. So i-multiply lang natin yan ng 1 times 10 raised to 6 para maging Newton per Newton millimeter. All over yung S sub X natin, which is etong nasa trial section natin na 416 times 10 raised to 3. So eto naka-Newton per millimeter na. So the value of our F sub B, or the actual, yung actual natin bending stress, that is equal to 157.91 megapascal. which is less than siya sa value ng allowable natin. Which is yung allowable natin is 163.68 megapascal. Therefore, safe siya sa flexure. Next naman is yung step FGH natin. Check naman natin siya sa shear. Dapat yung actual shear mo that is less than or equal siya dun sa allowable shear natin. So, since it is compact section, so yung FY natin, F shear natin, yung allowable shear natin is 0.4 of FY. 0.4 of 248. So we have 99.2 megapascal. So, para makuha natin yung actual shear stress, so that is VQ all over yung inertia multiplied by the VQ all over IB. So, yung pinaka-procedural lang dito sa pagkuha ng actual shear natin, shear stress, is yung pagkuha ng statical moment area, which is yung Q natin. So, mangyayari niyan is, imo-moment natin yung area natin with respect to the neutral axis. So, i-consider na lang natin is yung nasa taas na nasa taas ng neutral axis natin. So, mangyayari niyan, etong area na to, etong area na yan, is imo-moment natin siya dito sa neutral axis. Ganon din etong nasa wave. So, mangyayari niyan is yung area, imumultiply natin dun sa centroid para ma-moment natin siya dun sa neutral axis. So, meron tayong base ng flange na 102.36, yung thickness ng flange na 10.8, and yung thickness naman ng web na 6.16. Tapos, yung depth niya is 312.67. So, gagawin lang natin. So, kunin muna natin etong kalahati ng 312.67. So, that is 156.335. Next naman kunin natin is etong part na yan. So, eto 156.335 minus lang natin yung 10.8. So, that will become 145.535. So, let's solve for the value of our statical moment area. So, Q is equals to i-moment natin yung area natin sa taas. So, that is 102.36 yung thickness, that is 10.8. Tapos, yung distance ng centroid ng area natin dun sa neutral axis. So, that will become 156.335 minus yung kalahati ng 10.8 all over 2 plus etong maliit dito sa web natin. So that will become yung thickness natin na 6.60 multiplied by the width o yung taas na 145.535. So, tapos, yung distance ng centroid na to, ng section na to, dito sa neutral axis, that will become 145.535 all over 2. So, statical moment area is equal to 236.752.271 mm cube. And makukuha naman natin yung Vmax natin, di ba? Makukuha naman natin yan. Given naman yung I natin. And yung B naman natin, yun yung width na dinaanan ng neutral axis natin. So in our example, yung B natin is the thickness ng web natin. Kasi yun yung dinaanan ng neutral axis. So yung FV natin, FV is equals to, kunin muna natin yung Vmax. So that is WL over 2. So yung W natin is 14.859 multiplied by 6 all over 2. Tapos ito is imumultiply natin by times 10 raised to 3 para maging kilonewton kasi to. Para maging Newton. So, multiply natin yung Q na nakuha natin, 236,752.271 all over yung I na given or nakuha natin sa trial section, 65 times 10 raised to 6, and also yung B natin, which is yung thickness ng web natin. So, yung actual shear stress natin is equals to 24.17 megapascal. Which is less than siya dun sa allowable shear natin na 99.2 megapascal. Therefore, safe siya sa shear. So, sa last part natin is kukunin natin naman yung sa deflection naman. So, una, diba, check muna natin siya sa flexure. Pangalawa is i-check siya sa shear. And lastly is i-check naman natin siya kung safe ba siya sa deflection. So, since it is only a simply supported beam, kung ako sa inyo, i-memorize nyo na lang yung maximum deflection ng mga simple supported beams. Mga loads natin, yung mga usually nag-aakar para hindi na kayo mahirapan. So, in our example, so F, G, HI. So, last step. Dapat yung actual na deflection that is less than or equal siya dun sa allowable. So, para makuha natin yung actual, so since it is a simply supported, yung formula is 5WL raised to the 4th all over 384 EI. 5. Ano yung W natin? That is equal to 14.598. So, etong 14.958 in kilonewton per meter siya. Pero ang gagawin mo siyang kilonewton meter to newton millimeter, ganun pa rin siya. So, etong 1 kilonewton meter is equal siya sa 1 newton per millimeter. So, kahit hindi na natin siya, already converted na to into Newton per millimeter. So, yung tandaan nyo lang, using this formula, kailangan consistent tayo sa unit. Millimeter at saka Newton lang. So, yung length natin, that is 6 meter. So, gagawin natin siyang 6,000 para maging millimeter all over yung 384. Yung E natin na 200 gigapascal, convert natin siya into megapascal, i-multiply lang natin siya ng 1,000. Then, is yung I natin na 65 times 10 raised to 6. So, yung actual deflection natin is equal to 18.95 millimeter. So, yung allowable natin, sinabi dun sa problem na L over 300. So, yung L natin, that is 6,000 millimeter all over 300. So, we have 20 mm. Since it is yung less than sa allowable, therefore, it is safe. So, meaning to say, yung na-design natin, it is safe, therefore, adopt W12 by 22 for beam 1. So, eto na yung magsisilbing design natin. Na-design na natin yung biga natin.